EFI systems use electronically controlled injectors to spray the fuel. There are two basic systems: throttle body injection, also called single-point injection, and multi-point injection. Throttle body injection sprays fuel into the air as it passes through to the intake manifold. Multi-point injection has an injector for each cylinder, which sprays fuel directly into the intake valve port. The whole system has a fuel tank to store the fuel, a fuel pump to circulate fuel and provide pressure in the system, a fuel filter to clean the fuel and protect the injectors, a fuel rail or pipe to supply the injectors with fuel, injectors which spray into the intake valve ports, a pressure regulator to control pressure in the system, a throttle body with a throttle valve to control the flow of air to the engine, an air cleaner, ducting and an airflow meter to provide clean measured air, and a plenum chamber or surge chamber to dampen the flow of air. There's also an electronic control unit, a computer that receives data from sensors around the engine. It processes this data and uses the results to operate the injectors.
Because of the need to comply with exhaust emission regulations, the modern gasoline engine requires a fuel system of extreme accuracy and long-term reliability. A correctly matched air-fuel ratio must be available at all times and under all conditions. This is satisfactorily achieved by electronic fuel injection. EFI is a pressurized indirect injection system that uses solenoid-operated injectors with a fixed orifice. When they are energized, fuel passes through the injector body. This arrangement is called a multi-point system. One injector is located in each intake manifold runner or pipe adjacent to each cylinder. An electronic control unit, or ECU, opens the injectors by pulsing their electrical current. They spray fuel into each intake port directly in front of each intake valve. Fuel leaving the nozzle is atomized, and it mixes with the air also entering the system to form a combustible mixture. Fuel pressure is kept at a constant value above manifold pressure, so the amount of fuel injected is determined only by the length of time the injector is held open by the ECU. This is called the pulse width of the injector. The triggering signal to operate the injectors can be supplied from the ignition system or from crank angle sensors on the crankshaft or the camshaft. Engine fuel requirements change according to engine speed, load, and temperature, so the ECU needs information on these changes. Sensors measure these variables, then relay the information to the ECU in the form of electrical signals. The ECU then calculates the duration of pulses necessary to provide the fuel required. Extra fuel required during cold starting can be supplied by increasing the number of injection pulses, or by fitting a separate cold start injector that operates independently of the main injectors when the engine is cranking. The throttle body injection system, also called a central fuel injection system, has a single injector, or in some cases 2 injectors, mounted in a carburetor-like throttle body. The throttle body assembly is fitted to the flange of the intake manifold, and the fuel is sprayed into the intake air entering the manifold. The air-fuel mixture is then carried through the manifold into the engine. Fuel pressure is maintained at a constant value, and an ECU pulses the injector or injectors.
In multi-point injection systems, the air required for the combustion of the fuel is led from the air filter through the throttle valve and into the common manifold, or plenum chamber. From here, individual intake runners or pipes branch off to each cylinder. All of these pipes are of equal length. The design of the intake system determines how large an air mass can be drawn into a cylinder at any given engine RPM. This is where most advantage can be taken of electronic fuel injection, since it can achieve exactly uniform distribution of the air delivered to the cylinders. With unobstructed passages to each cylinder, the cylinder fills with air as efficiently as possible. The breathing of the engine, or its volumetric efficiency, is improved. The more air crammed into the cylinder, the denser the air-fuel mixture when ignition occurs. This increases the thrust on the piston and increases engine power output too. The temperature of the air influences how dense the air-fuel mixture will be. Cold air is denser than hot air, so it has a greater mass in any given volume. This is why on most intake systems, the air entry to the intake is away from engine heat, to ensure the entry of cool air. Since the manifold carries air only, it doesn't need to be heated by coolant. Filtered air arrives at the intake port as cold and dense as possible, ready for mixing with the fuel from the injector. The amount of air entering the engine must be measured so that the amount of fuel injected into it forms a mixture to suit the engine operating conditions at that time. The volume of air entering the engine varies according to the position of the accelerator pedal and the engine speed and load. Changes in volume are reflected in changes in manifold pressure between the throttle plate and the intake ports. When the pistons draw air away from the manifold more quickly than air can pass the throttle plate into it, the pressure in the manifold falls. At idle speeds, this pressure is low. A high depression or a vacuum exists. As the throttle plate opens, the pressure approaches that of the atmosphere. The depression or vacuum tends to fall in value. Devices measuring air entering the engine send a varying electrical signal to the ECU. The signal can be a measure of the volume of air or of the manifold pressure. In both cases, this information is combined with the engine speed signal to provide the basic setting for the injector pulse width. An airflow meter measures the volume of filtered air entering the engine. It can be mounted on the air filter casing or close by. All air entering the intake flows through the meter, then through a sealed flexible hose or duct to the throttle body, then enters the engine. Vane-type airflow meters have a spring-loaded vane or flap which deflects according to how much air enters. The electrical signal to the ECU varies with this deflection as contacts attached to the vane move across a potentiometer. The intake system must be airtight with no leaks downstream of the meter, otherwise inaccurate signals will be sent to the ECU. The purpose of any fuel supply system is to deliver fuel to the engine in a form in which it can mix with air to form a combustible mixture. The fuel must be finely atomized to mix with the air. This is why injection systems deliver the fuel under pressure. The EFI system is a circulation system. Fuel is drawn from the tank by a fuel pump and delivered to solenoid-operated injection valves. Fuel pressure at the valves is maintained by a fuel pressure regulator, and excess fuel flows back to the tank through a return line. The fuel filter is directional. It's fitted between the pump and injection valves to stop contaminants reaching other parts of the system. The fuel pump can be mounted externally on the chassis frame or submerged in the fuel in the tank. It's electrically operated and electronically controlled. It's driven by a permanent magnet electric motor, a sealed unit integral with the pump. Fuel flows through the pump and around the electric motor when it is running. There is never an ignitable mixture inside the pump housing, so there's no danger of explosion. The pump delivers more fuel than the maximum requirement of the engine, so pressure in the fuel circulation system is maintained at all times. A fuel pressure regulator maintains fuel pressure between the pump and the injectors.
In multi-point injection systems, the fuel pressure regulator has an inlet connection from the fuel rail and an outlet that lets fuel return to the tank. A control diaphragm and pressure spring determines the exposed opening of the outlet and the amount of fuel that can return. So the strength of the pressure spring determines fuel pressure in the fuel rail and keeps it at a fixed value. However, the pressure in the intake manifold varies considerably with changes in engine speed and with load, so the pressure drop across the injector must also be taken into account. For any injection duration, if fuel is held at constant pressure, then as manifold pressure varies, so does the amount of fuel delivered. That means fuel pressure must be held constant above manifold pressure. This is done by sealing the spring housing of the pressure regulator and letting it sense manifold pressure via a connecting hose. Then, when the manifold pressure alters, so does the fuel pressure. When manifold pressure is low, as at idling, fuel pressure is low. As manifold pressure rises towards open throttle, so does fuel pressure. Since the injectors are all subjected to the same pressure, they all inject an equal amount of fuel. The quantity of fuel delivered is thus controlled very accurately by the pulse width of the injector. Manifold pressure sensing is not required in throttle body systems, as the injection occurs above the throttle plate at atmospheric pressure. So fuel pressure is determined by the force of the regulator spring acting on the diaphragm. The injectors are sealed into the manifold by O-rings that prevent air entering at that point. The O-rings, together with plastic caps on the injector nozzles, also act as a barrier to heat being transferred to the injector body. For a short time after an engine is switched off, engine temperature keeps rising, and that can cause excessive vapor in the fuel lines. This pump stops this with a non-return valve on its outlet, which maintains the pressure in the fuel line during that short time. This pressure will decay over about 20 to 30 minutes, but it ensures effective hot starting characteristics. When the engine is running, the circulation of fuel ensures cool fuel is being delivered at all times, and vapor formation is prevented. The pump control circuit normally allows the pump to operate for a few seconds only when the ignition is switched on, and thereafter during cranking, and when the engine is running above a specified minimum RPM.
In multi-point injection, the injectors can all be triggered at the same time. This is called simultaneous injection, and the injectors operate twice per cycle. That's once each crankshaft revolution, each time delivering half the fuel for the cycle. In a 6-cylinder engine, the injectors are triggered on every third ignition pulse. In throttle body systems, the central injector is normally triggered on every ignition pulse. However, if there are 2 injectors, alternate triggering may be used. At idling speeds, the frequency may be less to provide finer control. The actual operating time of the injectors depends very much on battery voltage. The response time to lift the injector needle to the fully open position is about 1 millisecond. If battery voltage is low, this response time takes longer and the engine receives less fuel. The ECU can compensate for this delay in opening time by extending the duration of the injection pulse. In more sophisticated engine management systems, the control unit can control additional functions such as ignition timing, injection modes, idle speed, cooling fans, and fuel pump operation. To do this, however, more inputs are needed. To control ignition timing, some systems replace the distributor with a direct fire ignition system. Between one ignition point and the next, the ECU calculates when the ignition point will occur. It then triggers the ignition accordingly. Ignition can be varied according to load, speed, coolant temperature, cranking speed, and battery voltage. Identifying number 1 cylinder and the camshaft position allows different injection modes to be used. Sequential injection means injection occurs in the sequence of the firing order. Each injector opens once only in each cycle to deliver the fuel needed. Added load placed on the engine during idle can be compensated for by increasing the passageway of an idle speed control device. This lets more air bypass the throttle plate. This air has been measured by the airflow meter, so extra fuel is metered to maintain the same air-fuel ratio. The extra mixture thus delivered increases engine torque and maintains idle speed. For efficient operation of the catalytic converter, the mixture ratio must be maintained close to the stoichiometric ratio, 14.7 parts of air to 1 part of fuel. Efficiency of combustion can be monitored by measuring the percentage of oxygen in the exhaust gas. A high percentage may mean the mixture entering the cylinder is too lean. The oxygen sensor in the exhaust manifold, or in the engine pipe, tells the ECU how much oxygen is in the exhaust gas. The ECU then varies injector opening time to achieve a correct mixture ratio. Feedback also lets fuel settings change as components age. This is called adaptive learning. The ECU memorizes its fuel settings for different operating conditions and stores them for future use. If a fault occurs in a component or part of a system, a fault code can be displayed on the check engine lamp in front of the driver. Alternatively, a scanning tool can be connected to a diagnostic terminal, and information on the fault can be analyzed. Although most injectors operate at the nominal battery voltage of 12 volts, many sensors have a reference voltage of 5 volts. This is done by a voltage regulator in the control unit. It gives more accurate signaling, as fluctuations due to changes in battery voltage do not occur. The term stoichiometric ratio describes the chemically correct air-fuel ratio necessary to achieve complete combustion of the fuel. It's represented by the Greek letter lambda. The value of the ratio is 14.7 parts of air to 1 part of fuel. By mass, that's 14.7 kilograms or pounds of air to each kilogram or pound of fuel. So if lambda equals 1, the air-fuel mixture is at the stoichiometric ratio of 14.7 to 1. If an air-fuel mixture has a higher figure, say 1.03, there is more air in proportion to the fuel than 14.7 to 1, and the mixture is slightly lean. A mixture with a lower lambda value has less air proportionately than fuel, and the mixture is slightly rich. The exhaust gas oxygen sensor is also called the lambda sensor, since it can be used to maintain the air-fuel ratio at lambda equal to 1 within very close limits. It can be installed in the exhaust manifold, where it measures the percentage of oxygen in the exhaust gases. A high percentage of oxygen may mean too little fuel is entering the engine, the mixture is too lean, and lambda is greater than 1. The sensor delivers this information to the ECU, which adjusts the mixture accordingly. Similarly, a low percentage of oxygen may indicate too much fuel is entering the engine, the mixture is too rich, and lambda is less than 1. In an electronic fuel-injected engine, the fuel for the injectors must be pressurized before the engine can be started, so an electric fuel pump is necessary. This is an electric rotary pump. It can be located in the tank or externally on the underside of the body. Gasoline enters at one end and leaves at the other, so it is always full. This lubricates the pump motor and keeps it cool. The pumping element is a roller cell device driven by an electric motor. A rotor disc is mounted eccentrically in the pump housing. It has recesses around its edge containing metal rollers. As the disc rotates, Centrifugal force pushes them outward. This forms a rotating seal, and fuel is carried round in the cavities formed between the rollers. Because of the eccentric mounting of the disc, these cavities expand as they pass the inlet and contract passing the outlet. This pressurizes the fuel and forces it into the fuel line. The pump can also be an impeller type, which is less noisy. For a short time after an engine is switched off, engine temperature keeps rising, and that can cause excess vapour in the fuel lines. This pump stops this with a non-return valve on its outlet, which maintains the pressure in the fuel line during that short time. If a fuel blockage occurs further along the fuel line, it can overload the pump motor and make it overheat. So a high-pressure relief valve inside the pump lets fuel keep circulating. When the pump is mounted externally, a low-pressure pump can be used to supply fuel to the main pump's inlet. This low-pressure pump is mounted in the fuel tank. It's a centrifugal type and electrical, and it operates in the same way as the other high-pressure pump. It's very important to supply clean fuel to the fuel rail in EFI systems. Small particles of dirt can block an injection nozzle and cause an irregular spray pattern. Any water in the fuel will corrode the inside of the injector, especially if the engine stands unused for long periods. The first filtering occurs with a strainer or fine gauze in the fuel tank. The next filtering occurs at the inline filter, on the high-pressure side of the pump. This is a large capacity filter encased in a steel shell or an aluminum housing. This housing must be rigid to withstand the high pressures in the system. The filter is a pleated paper type with pore size of about 10 microns. A fluted support plate keeps the filter stable in the housing. The filter is directional, and it must be fitted in the direction of fuel flow. Final filtering occurs with a small conical filter at the fuel entry to the injector.
The fuel rail is a large section pipe with an inlet connection from the fuel filter. The injectors are attached to the fuel rail, so they are each subject to the same injection pressure. Then, when they're open, they each inject an equal amount of fuel.
In multi-point injection systems, the fuel pressure regulator is located on the outlet from the fuel rail. Fuel circulates continuously, but the fuel pressure regulator controls the quantity of fuel returning to the tank. This in turn controls the pressure in the fuel rail. It consists of a metal housing with a spring-loaded diaphragm between the two halves of a steel pressed shell. A valve attached to the diaphragm controls the exposure of the opening to the return line. With the pump operating, fuel pressure builds up on the underside of the diaphragm and raises it against the force of the spring. The central valve is carried with it, which lets fuel return to the tank. Fuel in the rail is now kept under pressure that's determined by the force in the spring. As well, further control is needed, as fuel pressure has to stay at a constant value above manifold pressure. Otherwise, the fuel quantity delivered won't be accurate. The spring housing above the diaphragm is sealed and connected to the intake manifold. Low pressure in the manifold then acts on the diaphragm and helps its movement against the spring. As a result, fuel pressure is continually corrected in step with changes in manifold pressure. When manifold pressure is low, as at idle, fuel pressure will be lowered. When manifold pressure is high, as at full throttle, fuel pressurizes. As a result, the quantity of fuel injected into the engine is set solely by the duration of the electrical pulse from the control unit. The auxiliary air device has a connecting hose from the intake air side of the throttle plate to its controlling passageway. A return hose then connects from the passageway to the plenum chamber. The controlling passageway is covered or uncovered by a blocking plate or disc, which is acted on by a metallic strip. The strip is heated electrically by a heater coil. The heating current is turned on when the engine starts. The heating effect bends the strip, which turns the blocking plate. As it turns, it changes the cross-section of the controlling passageway to control the additional air required. In a cold engine, the passageway is at its maximum set opening. Then, as the engine warms up, it gradually closes. The solenoid-type air control valve acts on signals from the control unit to bypass a measured airflow around the throttle plate. The position of the valve depends on how much current the control unit applies to the solenoid. Maximum current flow opens the valve fully to give maximum airflow. This is generally the assumed position for starting. Thereafter, the taper valve is positioned by pulsing the solenoid winding circuit at a predetermined frequency. The amount of valve opening, and therefore the amount of airflow, depends on the on time of the pulse. A long on pulse with a short off pulse will produce a high average voltage, and therefore a large opening of the valve. A short on pulse with a long off pulse will produce a low average voltage and a small valve opening. This on and off time is called the duty cycle, and it's generally expressed as a percentage. Variations in pulse width at the set frequency is called pulse width modulation. The stepper motor type of idle control positions its tapered pintle using a screw and nut assembly. The nut is part of a centrally located permanent magnet armature. It engages with the screw on the pintle. Rotating the armature extends or retracts the pintle, which closes or opens the air passage. Rotation occurs by switching current flow in two coils. The pintle turns in forward or reverse steps, numbered from 0, with the bypass air passage fully closed, up to 255 for maximum airflow. Such a large number of steps allows the pintle position to be finely controlled. When the idle speed is controlled by the position of the throttle plate, a DC motor may be used as a variable throttle stop. The controlling circuit can let current flow through the motor in either direction to extend or retract the linear actuator. Solenoid valves can also be used to bypass a predetermined amount of air around the throttle plate. These may come into operation for specific load compensation. For instance, when the air conditioning compressor is engaged. They open up a passageway of fixed dimension and do not vary the opening.
In engines with multi-point injection, the injectors inject fuel into individual intake tubes, directly in front of the engine intake valves. The injection valve, or nozzle valve, is held against the valve seat by a helical compression spring. A movable plunger is rigidly attached to the nozzle and supported in a guide in the lower section of the injector body. The plunger is acted on by a solenoid winding, wound onto the injector body. Each end connects to a terminal. The control unit completes the injector electrical circuit. It provides pulses of a set duration, so that the injector valve opens and closes or pulses very quickly. Electrical pulses pass through the injector winding and set up a magnetic field that draws the plunger and valve away from the nozzle seat. Fuel held under pressure in the fuel rail can now pass through the filter and the center of the injector and enter the inlet port. In a single-hole injector, fuel is injected in a finely atomized conical spray at an angle of about 25 degrees. The exact injector open time depends on the data the sensors give the ECU, but it usually varies from 1 to 20 milliseconds. Valve lift for the fully open position is about 0.15 millimeters and response time is about 1 millisecond. Rubber mouldings or O-rings seal the injector in the manifold and at the fuel rail. This helps prevent the transfer of heat to the injector and the formation of fuel vapor bubbles under heat-soaked conditions. Director plate injectors operate on the same solenoid principle. 4 minute holes for fuel delivery direct jets of fuel toward each other so that they collide and break up into a cone-shaped spray. In some engines with 2 intake valves, the injectors have 4 holes but only 2 jets directed towards each valve. This ensures good fuel distribution for efficient combustion and emission control. The jets are set very precisely, and they must be located accurately by means of the fuel rail. In side-feed injectors, the injector is located integrally with the fuel rail and fuel flows through the side of the injector near the bottom of the injector body. Fuel vapor is easily carried away by the return fuel, which provides easier starting when the engine is hot. Resin-molded connectors are used to reduce noise and to retain and locate the injectors in the fuel rail. All injectors are calibrated so that in any application, the nozzle valve lift and the annular gap between the nozzle valve and the injector body is the same for each injector. Fuel pressure is held constant, so the only quantity that can change is how long the nozzle valve is held open, and this is what determines how much fuel is delivered. This is called the pulse width of the injector and is decided by the control unit. The injectors fitted must have the correct calibration. Color coding of the terminal adapter can be used for identification. The injector used for throttle body injection is similar to that used for multipoint. It has a nozzle and spring-loaded plunger operated by a solenoid. When the injector opens, fuel is sprayed into the intake air, passing through the throttle body. There may be 1 or 2 injectors which open and close at a frequency set by the control unit. At low engine RPM, this frequency is low. As engine speed rises, so does frequency, until at some point the valve may not close completely, and then it may deliver an almost continuous spray of fuel into the intake air entering the manifold. In some cases, a cold start injector is fitted. It's a solenoid-operated valve on the intake manifold or plenum chamber. It is in the main airstream on the engine side of the throttle butterfly, and it's supplied with fuel under pressure from the fuel rail. A turbulence nozzle injects the atomized fuel into the airstream during engine cranking. The operation is controlled by the action of a thermotime switch.
The thermotime switch controls the operation of the cold start injector. It's fitted to the cylinder head casting with its lower portion immersed in engine coolant. This lower portion houses a bimetallic strip that reacts to coolant temperature. A heater coil is wrapped around the strip. Heating and cooling of the bimetallic strip opens and closes a set of contacts. This interrupts and completes the circuit for the cold start injector. When coolant temperature is below the rated value of the switch, the contacts are closed and so is the circuit for the cold start injector. Then, during cranking, the cold start injector will spray fuel into the manifold. If coolant temperature exceeds the rated value of the switch, the bimetallic strip bends and opens the contacts. That means that when the engine is above a certain temperature, the cold start injector won't operate, and this prevents excessive wetting of the spark plugs and a rich mixture on startup. The heater coil also limits the operation time of the cold start injector up to a maximum value depending upon the application. This can be about 10 to 12 seconds at a temperature of -20 degrees Celsius or -4 degrees Fahrenheit. The heater coil is energized during cranking, and if the engine fails to start within the specified time, the bimetallic strip bends under heating action and opens the circuit. This prevents flooding the engine with excessive fuel. The time limit is automatically reduced for temperatures up to the rated value of the switch. At that value, the contacts open under the influence of the coolant temperature.